Hello and welcome to another episode of Harvey Teaches You Chemistry. Today, entropy and Gibbs free energy. Everything in the universe is constantly trying to reach the lowest energy state it possibly can, because that's where it's most stable. Endothermic reactions seem to go against this, as they are raising the products to a higher energy state than the reactants. There must therefore be some sort of mechanism to compensate for this. This is called entropy. Entropy is a measure of disorder of systems. Systems that are more disorder have lower energy are at a lower energy. And we can calculate entropy of the entropy change of a system using delta S equals the sum of the entropy of the products minus the sum of the entropy of the reactants, and the units is in joules per moles per Kelvin. We're going to start off with an example of calculating the delta S of a reaction of calcium carbonate decomposing into calcium oxide and CO2. The values of calcium carbonate and CO2 and calcium oxide's entropy are given, so we simply add the entropy of the reactants together and take them away from the entropy of the products, which gives us 161 joules per moles per Kelvin. Gibbs free energy tells us if a reaction is possible. It combines the delta H of the reaction with the delta S of the reaction to tell us whether the reaction is moving to a higher or lower energy state. The equation is delta G equals delta H minus the temperature times delta S. We can use this fancy graph here, chart, to tell us whether a reaction is likely to be feasible at a glance. If the delta S is negative and the delta H is positive, then G is never negative, so reactions can't happen. Delta S is positive and delta H is negative, G is always positive, so reactions are always feasible. And for the other two values, it's temperature dependent. Let's now look at an example. Let's work out if the formation of calcium chloride is feasible at 300 Kelvin, which is roughly room temperature. The delta H of formation of calcium chloride is minus 795.4 kilojoules per mole. And the other three values there given are the entropy values of each of the compounds present. We can work out the delta S value using the method above, and it comes out as minus 269.6. We can now find our delta G, which is going to be minus 795.4 times 10 to the 3, because we need to convert it into joules, minus 300, our temperature, times minus 269.6, which is our S value for delta S value for the reaction. This comes out as minus, that's a big number. So yes, the reaction is feasible because delta G is negative. Another fun insight that delta G gives us is, as it always has to be negative, i.e. always moving to a state of decay, that means that the universe is slowly and irreversibly moving towards a state of decay, and there is nothing we can do except wait for its inevitable demise. Anyway, I hope you enjoyed this episode of Harvey Teaches You Chemistry. If you have any questions, ask them now or leave them in the comments, and I will see you next time.